Hello everyone. In this video we are going to talk about work. The complete details of work means what is meant by work, what are the different types of work, like that. So let us begin. So we'll start with understanding what exactly work or what when exactly a work is said to be done. So for that, let me give you a small example. Assume that there is a block placed on a surface which is actually at rest. This is at rest initially. Now, if you exert a force on this block, there may be two chances the block may move or may not move. If the force is good enough to move the block, then the block changes its position. It means the block gets displaced and move to the other position. Assume that it creates a displacement S. Then this force, this force, when it acts on a block, if it can create a displacement, then we can say the force has done some work. So a work is said to be done under the conditions that a force must act on a body and the body should be displaced. If these two things happen, then we can say there is a work done. And we can mathematically express work. We represent work with W, and we can mathematically express work as product of force and displacement, because more is the force and more is the displacement, then more is the work done. Either force is large or displacement created is large, or both of them are large, then we can say a large work is done. So mathematically we can express work done as product of force and displacement. But this is not the case every time. Let's take another example. Assume that when a block is placed on a surface, if a force is acting on it this way. In earlier case, the force was acting horizontally. But this time, this force is acting at an angle theta with the horizontal, like this. Assume that because of this force, if the body or the block displaces by this much through a displacement S, then what is the amount of work done in this case? If you think it carefully, this time this displacement, yes, who created this displacement? If you think it carefully, this force, unlike the previous case, it's not entirely acting in the horizontal direction. It was making an angle, it is making an angle with the horizontal. So the total force F is not contributed in the horizontal direction. To find the contribution of the force in any particular direction, as force is a vector physical quantity, we have to resolve it. If we resolve, the component of force in the horizontal direction is F cos theta, and the component of force in the vertical direction is F sin theta. After resolution, we can clearly say that F sin theta, this component of force is definitely not acting along the direction of displacement. So this is not reason. F sin theta is definitely not the reason for this displacement. F cos theta is a component which is acting along the direction of displacement. So we can simply say that F cos theta has created this displacement. So what I simply say is, when a force F is acting obliquely, a part of it acts along the horizontal, a part of it acts along the vertical. Out of these two, only one component is contributing for the displacement, which is F cos theta. So this time we can write the work done as product of force and displacement, but this time the amount of force which is contributing for the displacement is F cos theta and the displacement is S. Then we can generalize and write it as Fs cos theta, then we write it as F bar dot S bar. We know that the formula of dot product A bar dot B bar is equal to AB cos theta, where theta is the angle between A bar and B bar. Here if it is Fs cos theta, we can similarly write it as F bar dot S bar. So this is the most general formula for the work done. So work done is given by Fs cos theta, which is also equal to F bar dot S bar. That is the mathematical expression of work done. Now if we look at the units of work done, let us write CGS units and MKS or SI units. If we write that, as the formula of work done is equal to force multiplied by displacement, to write the CGS unit of work done, we know the CGS unit of force is dyne multiplied by CGS unit of displacement is centimeter. Therefore, the CGS unit of work done is dyne into centimeter, which can be simply written as erg. So CGS unit of work can be called as erg or dyne into centimeter. And when coming to MKS or SI unit, the SI or MKS unit of force is Newton multiplied by the SI or MKS unit of displacement is meter. Therefore, Newton into meter is the SI or MKS unit of the work, which can also be simply called as joule, and it is represented by J. Joule is a scientist name. And if we try to look at the conversion of SI unit into CGS unit, which means if I ask you 1 joule is equal to how many erg, how to answer this question? Simply, I take 1 joule is equal to nothing but 1 Newton into meter. This one, I took it from here. We know that 1 Newton is 10 to the power of 5 dyne, and 1 meter is nothing but 10 to the power of 2 centimeter. We can write it as 10 to the power of 5 multiplied by 10 to the power of 2 gives us 10 to the power of 7 and dyne into centimeter. Therefore, 1 joule is equal to 10 to the power of 7. This dyne into centimeter can be written as erg. Therefore, the value of 1 joule is equivalent to 10 to the power of 7 erg. This is the conversion of SI unit into CGS unit. And we can also note that as work done is written as dot product of two vectors. What is meant by dot product? Let us see here. Work done is written as dot product of force and displacement. This is a dot product. What is meant by dot product? Dot product is the product whose result is a scalar. That's why this is also called as a scalar product. As work done is written as a dot product of two vectors, that's why we can say work done is a scalar quantity. It's a scalar quantity. Let's quickly revise what have we learned till now. First thing, we understood work done on a body depends only on two things. They are force and displacement. As it is directly depending on force and displacement, it can be written as product of force and displacement. And the more general formula of work done can be written as F bar dot S bar, which is equal to Fs cos theta. Then the CGS unit of work done is equal to erg. SI unit or MKS unit of work done is equal to joule. We also have seen that 1 joule is equal to 10 to the power of 7 ergs. This is what work done and the mathematical expression and units of work done. And now quickly see, let us see what are the different types of works. For this, to understand what are the different types of work, what I do is I will take a few simple cases. Let me assume a situation that if there is a block placed on a surface, and assume that it's not just placed, assume that it's already in motion with a speed 10 to the power of, sorry, 10 meter per second. It's moving with a speed 10 meter per second. In addition to its motion with a 10 meter per second speed, if you assume that a force is applied on it, a force starts acting on it, we all know, we can guess what happens. Due to this additional force acting on the block, which is already in motion with a 10 meter per second speed, the speed of the body increases. It may rise to 10-20 meter per second or other higher values. So what happened here? When a force starts acting on a body which is already in motion, it changed its speed. As it is acting in the direction of motion, the speed of the body increased. In this case, what happened? The body is already moving towards right, means its displacement is towards right, and a force is also acting on it in the right direction. The angle between them is 0 degrees. The angle between force vector and the displacement vector is 0 degrees. Thus, if I write its mathematical expression Fs cos theta, the 0 of cos is nothing but 1. That's why we can write Fs. Therefore, work done is equal to Fs with a positive sign here. Why did I write positive sign especially? Let us see that in the coming discussion. Let us take another similar situation. If a block is moving on a surface with a similar speed 10 meter per second, but this time assume that a force started acting on it in opposite direction. So the force is acting in a direction opposite to the direction of motion, not in the same direction like the previous case. Now guess what happens? We can simply say that as the force is trying to pull the body back opposite to its direction, its speed starts reducing. Finally, the speed becomes 0 and the body comes to rest. In this case, what happened if you observe carefully? The body is already displacing in the right direction, but a force started acting on it in the opposite direction, where the angle between the two vectors, force and displacement, is equal to 180 degrees. If you try to analyze it mathematically, Fs cos theta, the 180 degrees of cos is -1. That's how Fs into -1, the work done is equal to minus Fs. Hope you understand why did I write positive sign there particularly. Now we can see the difference. When the force is acting in the direction of motion of the body, then the work done came out to be positive. But when the force started acting on a moving body in a direction opposite to the direction of motion or velocity, then the work done came out to be negative. Why positive? Why negative? What is the logic behind that? Let us understand. When the force is acting in the direction of motion, velocity of the body increased. Velocity of the body increased. That's why this work done is positive. So the work done by a force which is acting in the direction of motion is called positive work. It's a positive work. But what happened when a force is acting opposite to the direction of motion? When it is acting opposite to the direction of motion, the speed of the body decreased. The speed of the body decreased and came to rest. That's why you see a negative sign here. That's why the work done by a force which is acting opposite to the direction of motion is said to be negative work. Very simple to understand. If the force is in the direction of motion, it increases the speed, the work is said to be positive work. If the force is acting opposite to the direction of motion, it decreases the speed and the work is said to be negative work. That's how we can classify the work as positive work and a negative work. First case is regarding the positive work and the second case is regarding the negative work. Let us see a few situations or practical examples for this positive work and negative work. Assume that your friend is riding a bicycle. Look at this. Your friend is riding a bicycle. He is already moving with a speed 10 meters per second, like previous example. Now you started pulling the cycle from behind. You applied the force on the bicycle in the direction in which already it is moving. Now guess what happens? We know that the bicycle starts moving rapidly. The speed of the bicycle increases. So whenever force acts on a body, if the speed increases, that work is said to be positive work. So this is the example for positive work. Very simple example, real life example. We'll take a similar case. If the same person is moving with a velocity 10 meters per second on the bicycle, again this time what you did is you started pulling the bicycle back. We know that if we start pulling the bicycle back, what happens? The speed of the bicycle gradually reduces and it comes to rest. The speed decreases. And if in any work, if the speed decreases, if the force decreases the speed, the work done by that force is a negative work. So this is a simple example for negative work, positive work and the negative work. These are the two types of forces. Let us see another different type of case. We'll investigate another case, third case. Assume that a person is standing with a big load on his head, maybe a bag on his head. Assume that he stood there for 30 minutes. How do you feel if you stand with a bag on your head? We feel tired. We assume that we feel like we have done a lot of work. But according to physics, which is written as product of force and displacement, yes, there is no displacement for the bag. The displacement of the bag is zero. There is no work done. The work done on the bag is zero because there is no displacement. But you may feel that you have done a lot of work. That's a biological work. You consumed your chemical energy of the body and you did a biological work. You may feel you're tired because of that work, but according to physics, mechanically there is no work done. So a work is said to be done only when there is a displacement created on the body. And we'll see another situation. This is one case where we can see the work done on the body is zero, though there is a force. There is a force, but the work done is zero. We'll see another case. Assume that a ball is moving with a speed 10 meters per second. It's moving like that. If you assume that there is a force acting on it, like this, observe this. This force, unlike the previous cases, neither acting in the direction of motion of the body nor opposite to the direction of motion of the body. It is entirely in a different direction, which is if the body is moving this way, the displacement is in this direction, but the force is in the upward direction. You can simply say the angle between them is 90 degrees. Means what? The force is acting perpendicular to the direction of motion. In the earlier two cases, you have seen one case force is acting in the direction, the other case it is acting opposite to direction. But this time it is neither acting in the direction nor opposite direction. It is acting perpendicular to the direction of motion. What happens now? If you see mathematically this case, if you observe it mathematically, I will remove this. Theta is 90 degrees. We know that work done is Fs cos theta, but 90 degrees of cos is 0. That's why Fs into 0, the work done comes out to be 0. This is another case where the work done is 0, though there is a force acting on the body. In this case, there was a force acting on the body. The person who is carrying it is applying a force in the upward direction, but there is no displacement. That's why the work done is 0. In this case, present case, there is a force acting on the body which is perpendicular to the direction of motion, but still the work done is 0. Let us try to understand this little carefully. What is happening here? What is this force doing? If you observe carefully, this force which is acting perpendicular to the direction of motion, this is neither increasing the velocity nor decreasing. When will it increase the speed? If any component of it or the force directly acts in the direction of the motion. Or if the component of force is acting opposite to the direction of motion, then the speed decreases. But none of them is happening. As the force is completely perpendicular, no component of this force is acting either in the direction or opposite direction. So, where is this force going? What is it doing? Rather than increasing the speed or decreasing the speed, as it is not in the direction of motion, what it can do is it is simply changing the direction of motion. So on whichever the body, the force acts perpendicular to its direction of motion, the body's speed will neither increase nor decrease. What happens? It simply remains the same, but the direction of motion changes. Now, the body on which the force acts perpendicular to direction of motion, it starts negotiating a circular path. Now it goes in a circular path like this. It will revolve in a circular path. So what does a perpendicular force do? A perpendicular force, it neither increases the speed nor decreases the speed, but simply changes the direction of motion. Yes, there is no change in speed. If increases the speed, positive work. If it decreases the speed, negative work. But it is neither increasing the speed nor decreasing the speed, but just changing the direction. Yes, there is no change in speed. No change in speed. There is no work. That's why work done is 0. Hope you understand why the work done is 0 when force is acting perpendicular. The speed is neither increasing nor decreasing. As the force failed to create any change in its speed, so the work done is 0. But where does this force go? This force will change the direction and makes the body negotiate a circular path. You may ask me, though there is no speed, there is a displacement. But if you observe carefully, if the body starts here, after every revolution it comes to the same point, where the displacement is 0 again. That way also you can say the work done is 0. So finally, though there is a force, if the force could not create the displacement, if the displacement is 0, then the work done is 0. Though there is a force, if the force acts perpendicular to the direction of motion, then speed neither increases nor decreases. As the force failed to change the speed, there is no work done due to that force. But the force simply make the body revolve in a circular path. The best example for that is planets revolving around the sun, Earth revolving around the sun. What happens here? The gravitational force is acting along the line joining them, and the planet Earth is moving in this direction, and the force is acting perpendicular to it. The gravitational force is perpendicular to it. So thus, the speed of the Earth neither increases nor decreases, but the direction of the motion of the Earth changes. That's why it negotiates a circular path. Circular or any other comes in the future discussions. So basically, it changes the direction, not the magnitude. That's why the work done by this gravitational force is 0. So these are the example. This is the example for 0 work done. So now let us revise quickly what we have discussed about the types of work. So this is work. Yeah, this is positive work, and here I write negative work, and here I write zero work. When the work is said to be positive, simply when force and displacement are in the same direction. What happens then? The angle between them is 0. When a work is said to be negative, simply when both force and displacement are in opposite direction and the angle between them is 180 degrees. When is the work said to be zero work? When force and displacement are perpendicular to each other, when theta is equal to 90 degrees. What are the consequences of these different types of forces? What is the consequence of positive? Oh, sorry. What are the consequences of these different types of works? The consequence of positive work is speed of the body increases. So whenever a positive work is done on a body, definitely you will see a increment in the speed of the body. What about the consequence of a negative work on a body? What happens? Speed decreases. So a work is said to be negative by a force if the speed of the body decreases due to that work. And what is the consequence of zero work? It neither increases the speed nor decreases the speed. Speed remains speed remains same. But what happens? Just direction changes. This is what the detailed discussion about work done and different types of works along with their relevant examples. Thank you very much. We'll meet with the further discussions of this lesson work and energy in the coming videos. Thank you very much.